Okay, great. Hello, everyone. And thank you for having me. Sorry that I could not be at the venue, but I think it's a great opportunity, and I'm also happy to see some familiar names and also get to know some new ones. I was told that we are already a little bit over time, so I'll try to be a little bit faster. But also allow me to start by acknowledging the help of my colleagues here, as you can see, my colleagues at Nokia Bell Labs, who helped me with preparation of the material. Um, so let me start with a brief introduction. The previous speakers talked about this too. So we are addressing what we call a reconfigurable intelligent reflective surface. So all of the three adjectives are relevant, and you will see in the literature people referring to those as RIS or IRS. And to avoid the negative connotation of paying taxes, I will try to stick with the first one, the RIS, throughout this presentation. But this is generally, they both refer to the same thing more or less in the literature. So what is a RIS? These are usually metallic surfaces which are reflective and are sitting on a dielectric panel, or they could be also meta surfaces. The goal is to have a software-defined dynamic control over the reflection pattern of these surfaces, which essentially creates a potential for anomalously varying the phase and in some cases amplitude and frequency of the reflection. That is being mostly the premise of the research in the literature. There is, however, also potential for doing better RF sensing. But my talk will be mainly focused on the communication aspects of this. So essentially, the bottom line problem that we are addressing is that, so as a telecommunication research community, for decades, we have been working on optimizing the operation at the endpoints of the communication link, so the transmitter and the receiver. And now we want to know how much gain is there if we try and control the radio propagation environment too. So, and what will be the cost associated with that? So let's start maybe with the first part of that question. What is the potential gain from a reflective surface? To answer this, let us picture a simple scenario like this. So I have, and it's a common scenario as well in the literature. So you have a urban street intersection scenario. There is a transmitter and there is a receiver on the other end. The role of the reflective surface is essentially to redirect and reflect the radio signal from the base station to the user and back. We can start with a simple model like this, and one can use the available toolkit in EM theory. For instance, in this case, we can use the Kirchhoff approximation, and then you can calculate what would be the path gain through this composite link of transmitter, RIS, and receiver. We can come up with a plot like this on the left-hand side. And let's go through this plot. The x-axis is essentially the corner receiver separation, so the distance between this corner and the receiver. And the y-axis is showing the path gain between the transmitter and the receiver. So the transmitter is essentially fixed. The first curve that you see at the bottom, this is the universal theory of diffraction around the corner. This is what that theory will give you. And admittedly, this is a more common benchmark that is used in the literature for RIS studies. But in practice, if we look at what empirical measurements show us, which is something similar to the curve that you see, the black one, the dashed black one. This is a New York City measurement. And the channel is actually not as bad as the corner diffraction model could predict. So there are actually more advanced models that can predict this, similar to this empirical measurements. For example, this blue line that you see here, this one considers that there are 4 octagonal utility poles. There are reflection from there's reflection from the rough surface of the walls, and combines those, and we see that it's closer to the to the empirical measurements, which also suggests that this is a more reasonable, so to say, benchmark to compare risk against. Now, if you go back to our risk problem and assume, let's say, in this plot, you see the 0.3 by 0.3 square meters of surface for the risk, and this is at 28 gigahertz, by the way. And let's assume that there's perfect CSI available, an ideal scenario, geniated, if you will. We can come up with this curve in the middle, and this is, if we compare it with the realistic benchmark, it seems that the gain is on par with what you get as existing, what we call ambient scattering in the environment. If you applied the same curve for a 1 square meter of surface, which is around, let's say, 9 times the larger surface, around 20 dB more gain, you will get a gain that similar to what you would naturally expect from a adding something to the net. So what that means is that essentially the surface should be large enough in order to provide a gain which is sufficiently higher than the existing ambient scattering, as I mentioned. What is also crucial in here is this green line that I just that just appeared on the slide. So the assumption of perfect CSI. In fact, if you account for the lack of full channel state information, which effectively was one of the questions that was just being asked, the channel is not line of sight. It's actually multipath. Even in higher frequencies, there's a lot of multipath and reflections, which the effect of it is that it widens the beams, if you will. And in this case, for instance, I'm showing how much you will lose if the beam of a 1 square meter surface is widened to 5 degrees. So it's bottom line is that the surface area is really important, it should be large, but at the same time, channel state information is also very critical. Now, I mean, that impact that I was just talking about in terms of lack of full CSI can be explained in terms of angular spread, which shows the multipath richness of the channel. The large risk aperture creates a very narrow beam. However, if the angular spread of the channel is much wider than those beams, which we learned that in practice it is, then a lot of that gain is going to be lost. Here you see 2 examples. One is in urban measurements and the other is in indoor factory measurements. What we observe is that essentially the angular spread for urban environment could be as large as 4 degrees median. And inside a factory could be as large as 8 to 15 degrees of spread, depending on the factory and how much reflective metallic surfaces are in there already. Therefore, inside the factory where there's all of this significant amount of reflections available, things get even more difficult. So I have some example in the back of the slides. If we will have time, we'll show them, but it's even more difficult inside a factory to see significant gain from risk. Now, okay, so this is basically just to propose another way of operating risk, sort of to avoid a lot of the difficulties with acquiring CSI and reconfiguring things based on it. This approach requires minimal CSI. This is similar to the analog grid of beam that we have in new radio, and one could essentially define a grid of beams, pre-configure them at the risk, and the best one out of those would be chosen for each user one at a time. So essentially, you cannot have too many of those. So that already tells you that beams are going to be wider than the aperture of the risk can generate. But again, the very important message here is that again, we need very large surface areas, but the complexity should not scale with the size. So a beam-based approach is perhaps a remedy to this sort of problem. It curbs the complexity, if you will, and it does not scale with the size. Okay, so let me maybe share one last point of concern here. And this is in regard with the modeling, was also referred to in the previous talk. So when deploying risk in any communication system, whether it's simulation for a research work or it's optimization in an actual deployment of the risk surface, the risk needs to be modeled accurately so that based on the collected CSI, we can adjust and reconfigure the elements, whether it's a lump impedance connected to them or varactor diodes that needs to be turned on and off. Either way, we need to have a proper model of the risk. What was shown by one of our former students is that, first of all, some of the existing modeling of risk in the literature have some inaccuracy, which in some cases could actually be within 6 dB gap to what risk can actually deliver. But what is more important is that if the inaccurate model is used to configure risk, then the received power from risk could even be further lower than what the model predicts. So the gap could, for instance, in this example that we have tested for 1 square meter of risk, could be as large as 14 dB. So the modeling is very crucial as well. And here in this slide, I just want to raise one more challenge, which is about hardware implementation of risk. Some of the aspects were already addressed in the previous two talks. This is simply to say that realizing what is generally assumed in the literature, which is a fully adjustable lump impedance, which is connected to each of the reflective elements, which can then be adjusted flexibly and in no time. That assumption is pretty much too costly to practice. Perhaps a more reasonable approach is to assume that the phase shifters are quantized, and then you can assume like one or a few bits of configurability per element. Which, by the way, that quantization in phase shifter already takes some of the gain that theoretically you would expect from RES. And this is essentially my last slide. Allow me to summarize sort of and also conclude in the same slide. I will do this by looking at the matters of cost and complexity and what I call functionality for risk. So what I'm sharing here, let me bring all the three categories up here. This was to some extent already also addressed from different points of view in the past two talks. The more we go to the right-hand side of what I have on this slide, the functionality is improved and the cost also increases. These are, I mean, qualitatively addressed. So I don't have any numbers associated in dollars to the cost, but you can imagine the cost increasing with the functionality. The first category on the left-hand side, this is perhaps the simpler one. I believe it was referred to as passive risk in the first talk. This is a non-intelligent and let's say a dumb reflective surface. This is a reflective surface that is pre-configured, and it can only create one reflection pattern. So in a way, this is, you can imagine it being similar to the concave mirrors that are very common at the entrances of driveways here in New Jersey, I guess in California as well. There's no control for tuning and configuring the risk. And it is a low-cost print and post, as I call it, type of reflective surface. And perhaps anyone can at some point build it at home. You can use it to patch up, let's say, a small coverage area, a small coverage hole. You can use it to improve Wi-Fi coverage at home, or things like that. The second category in the middle is what I call limited reconfigurability. This one does not need to be highly intelligent, but it needs some level of processing because there's a control link between the RIS and the network, and the RIS needs to understand what those control messages mean and how to interpret them into a configuration for a reflection pattern. This category is similar to what the grid of beam example that I shared a few slides back. So it can potentially be used in that around the corner sort of street cross-section example that I shared before. So you can enhance coverage with a large enough surface of this size, of this type. And then there's the third category all the way on the right-hand side, which is, by the way, the most addressed category in the literature. And it essentially assumes that RIS is intelligent to be fully reconfigurable. It has the ability to sense the channel from the receiver and the transmitter, and it has the ability to adapt to the channel So it requires a high rate control link to the network. And in some papers, I've actually seen that this category is assumed to be equipped with artificial intelligence. So in other words, this third category, if you will, is pretty much some sort of a base station or a smart relay without the power amplification. Okay, so with this, I would like to conclude by saying that so it is important both for the research community and for the industry sector when we talk about risk to be more clear which one of these categories we're talking about and to take into account realistic channel modeling, realistic risk modeling, and also to have in mind how feasible it will be in practice to realize those assumptions. Yeah, so thank you so much. I'll be happy to take questions if any. By the way, I cannot hear any sounds. I don't know if there's any problem on my side.
Hello, can you hear me?
Oh, yeah, now I can hear you.
Hi, very, very nice talk. I really like the fact that you took a skeptic's point of view. You looked at what can or cannot be done and kind of hashed out these three functionalities or three possibilities of using them in fully, partially, etc. reconfigurable mode. My question is, you mentioned that signal processing can play a big role in this fully reconfigurable setting. So let me tell you, in conventional phased array antenna arrays, a big advantage is that I can do digital beamforming. And what it means is that, I suppose I want to do something like adaptive beamforming or minimum variance distortionless beamforming. It's a very popular technique in radar to kind of, maximize your signal to interference plus noise ratio. So offhand, I do not know what beam pattern I'm going to generate. I collect the data and I solve an optimization problem and gives me the weights that I want to realize, okay? And then I can tune my digital signal, which is at the output of this phased array, and then apply the weights digitally and somehow get the digital beamforming done. How do you envision doing this with a RIS like this? What will be the processing steps to kind of envision this?
A very good question, and in my opinion, this is perhaps the main question that needs to be solved for risk to be practical. Mm-hmm. When my friend Marco Di Renzo has done this analysis in details, so it's not my work, but I would refer to it, that you can essentially collect CSI either at the network or at an intelligent risk, mm-hmm. In real time, and then do the same type of phase shifter type of beamforming for the instantaneous channel that you have essentially collected and estimated. But the challenge is that, first of all, as I mentioned, the risk surface needs to be very large. So at 28 gigahertz, you can imagine easily easily thousands of elements, right? Mm-hmm. Could be as large as for 1 square meter, I believe that's like 4,000 elements, if my math is not too wrong right now. So the overhead that corresponds to that, it increases significantly, and the capacity gain that you get from adding the risk, it basically is nullified. It canceled out by the overhead that you're adding to the system. So it's very challenging. That's why, in my opinion, the approaches that go with reconfigurability in real time are very difficult. Very difficult to realize in practice.
No, totally makes sense.
Yeah, and not to mention how challenging and costly the hardware is going to be to build it when you want to have a reconfigurable circuit that in very low latency can respond to the variations in the channel.
Yeah, and all the errors that you said that comes from modeling, inaccurate modeling, the near field of the risk will somewhat be pronounced also at the digital level, because you're quantizing on top of that, right? Depending on how much you quantize, because you may want to coarse quantization because there are so many of the elements to save the complexity. So there is a very delicate balance there.
Absolutely.
Right. Thank
Absolutely.
you. Yeah.
Thank you very much. Thanks.